From the beautiful studios of Way Happy, this is Mr. Meyer, and we're doing 9-3 probability. So let's get started. You know how to do probability. What you have to look toward in the middle of this box here is that probability, really, of an event is equal to the number of, you got to count the number of successful ways to do something divided by the total number of ways. And that is what probability is. But sometimes that can get a little confusing, or there can be many ways that we can count stuff. Some things you should know. Probability is a fraction. It's always between 0 and 1. It can include 0 and 1. 0 meaning it's the empty set. It's never going to happen. 1 being that it's always going to happen. All the probabilities that you have for an event, they should add up to 1. So make sure that you can always check. Now, let's do a little bit of probability, and you can read over your notes and see that. But we got Dylan opens a box of dozen chocolate creams, and he offers 3 of them to Russell. Russell likes vanilla creams the best, but the chocolates look all the same on the outside. If 5 of the 12 creams are vanilla, what is the probability that Russell picks vanilla? So again, what do I want to do here? I want to know the probability that Russell picks 3 vanilla. And what do I have here? Well, the success is that he picks 3 of 5 vanillas. And the total is that he just picks 3 of 12 chocolates. Right? Chocolate's a general term. Vanilla and pure chocolate combined together. So how many ways, now let's count. How many ways can you pick 3 of 5 vanillas? Well, I don't care about their order, so I'll use a combination. 5C3. And how many ways can you pick 12 chocolates from 3? Well, I'm going to use a combination, 12C3. And that will give me, on a calculator, 1 over 22. And I cheated because I already did it, and you can see it right there. But that will give me a 1 in 22 chance that he will pick vanilla, vanilla, vanilla. Now, another way you can see on my calculator how I did it, because I know some people will like to do that, where they will use the probability, and this is actually sneaking ahead, but it's kind of some things going on. Another way to do 3 vanilla is to say, well, what's the probability of vanilla, and then a vanilla, and then a vanilla, given that you've already done it. Well, the probability that you get that first vanilla, we know 5 out of the 12 are vanilla. And then the probability that you get a second vanilla would be 4 out of 11. And that's like a little condition there that we have lost one of the chocolates. So that's why there's only 11 now. And in fact, we've lost one of the vanillas. There's only 4 now. And now we multiply that for a third time, 3 over 10. And you will notice that that also gets you the 1 over 22 because it's the same problem. But the chance that you get vanilla, 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 you could break it down and either do a combination, or you could just do each one individually using the power property. So what about this? If you flip a coin 3 times, what's the probability of getting all tails? Well, you got a couple options again. You could write out all the possibilities. I know that we could get heads, heads, heads. I know I could get heads, heads, tails. I could get heads, tails, heads. I get heads, tails, tails. I could get tails, heads, heads. I get tails, heads, tails. I get tails, tails, heads. Or last but not least, tails, tails, tails. Look at that. 1, 2, 3, 4, 5, 6, 7, 8. So there's a total of 8 outcomes. And how many are all tails? Just one of those outcomes. So there it is. Or maybe you don't like that, because what if it would have been a lot more coins and I don't want to do it all? I could have just said, well, the probability of tails and tails and tails. Well, probability of 1 tail is a half, times probability of a second tail is a half, probability of a third tail is a half. Multiply it all together, you get a 1 in 8 chance that you are going to get tails, tails, tails. All right, let's keep moving on then. We're on a roll. Sometimes we have probability that they have to happen in succession, and that's really kind of what we've just done up here. This first one, if they're independent, meaning like the flipping of the coins, then you can just multiply the probabilities together. What's the probability of tails? What's the probability of tails? What's probably the 2 coins do not depend on each other. It's not like, oh, something happened. We got tails, so now the second coin's like, oh, I'm not going to be tails because we were last time. No, they are totally independent events, and therefore this little property holds true. You can just multiply them together. Now, there's also sometimes that they're not independent, kind of like that other example up here, right? They weren't independent. They did have something to do with each other. Once he pulled a vanilla, the total number changed of chocolates in the thing and vanillas in the thing. So they were dependent events. Like whatever happened in the first one changed it. And so that's where you have to take this part into account. This is read as the probability of B given that A has already happened. So that's what this says. What's the probability of B given A happened? And so in other words, we already pulled a vanilla, so now what was the probability of another vanilla? And so that's why we increased it down. Big thing to notice is that and means multiply, right? So or usually means you're going to add probabilities together, and means you're going to multiply probabilities together. Excellent work. Now let's talk about some probability tools that help us. There are things called Venn diagrams that they help. You draw a Venn diagram to try to organize your data. You could draw a table if you like. And there's also tree diagrams that are useful. So I'm going to give you an example of each one of those. So here's my example for a Venn diagram. It says in a large school, 54% of the students are girls and 62% of the students play sports. And half of those girls play sports. So I would have like a Venn diagram that says, all right, here's the girls, and I have information about the girls in sports. Here's the people that play sports, and I have some good information. I know in the girl bubble, 54% of the people are in the girl bubble, and I know that 62% of the people are in the sport playing bubble. And by the way, this means since the girls are 54%, everything outside is 46%. So that's kind of nice to know. But there's a little confusion here with the sports. There must be some overlapping of people that are sports and not. And that's why they give us a little more information. They say half of the girls play sports. So in the girls bubble, 54% are girls. Well, half of those play sports. So I'm going to sneak them in this bubble, 27%, which means I'm going to change this to 27%, half and half, right? So now half of the girls are just girls, half of the girls are girls that play sports. So there's all 54 girls still in the girls bubble. Now in the sports bubble, I've kind of messed it up a little bit. Now I have like 89% of the people playing sports, and that's not true. It's only 62. Some of them are girls, some of them are not. So I need to fix that too. I got to take away 27%. So that would leave me with 35% play sports. Now look, 35% of those would all have to be boys out of this group of 46. So that means that there are 11% of boys that do not play sports, and that's our entire gender breakdown. And now you have a really nice breakdown. You can double check your numbers. 54% are girls, awesome. 62% play sports, and adds all up to 100%, like probability has to add up to 100%. So I'm feeling really good. And now I can answer any questions with this beautiful Venn diagram. I can say, what percentage of the students who play sports are boys? All right, so I can already tell you that's right there, right? 35%. So for part A, I can tell you 35% are boys. Part B, if a student is chosen at random, what is the probability that it is a boy who doesn't play sports? Well, look at my Venn diagram. Where are the boys that don't play sports? I got girls that play sports, I got boys that play sports really, and then down here I have boys that don't play sports, and I would say 11%. And so you can see we had to do all the math kind of early in the Venn diagram, but then screaming out the answers was much more simple. So Venn diagrams can really help a ton. Also, I love tree diagrams. And so here would be a tree diagram, and this one's a little tricky. You have two identical cookie jars on the counter. Jar A has 2 chocolate chip and 2 peanut butter cookies. Jar B just has a chocolate chip cookie. if we pick a cookie at random, what's the probability that it is a chocolate chip cookie? So it's a pretty tough problem. So what I do is I go, all right, well, you got jar A and you got jar B, right? And since they are identical, I'm going to put the probability of their chance happening on each of their arms here. So you have a 50-50 chance. So I'm going to say a half and a half. 50-50 chance of going to jar A, 50-50 chance going to jar B. I don't know which one you're going to do. Inside jar A, though, I have two options. You are either going to pick a chocolate chip cookie or you're going to pick a peanut butter cookie. And the chance that you pick a chocolate chip in jar A is 2 out of 4. I guess I'll put that even though I really want to write 1/2. The chance that you put a peanut butter cookie is 2 out of 4. And so now the chance that you go to jar A and pick a chocolate chip is 1/2 times 1/2, which would be a 4th probability that that happens. So I multiplied because it was and jar A and chocolate chip. Same thing with jar A and peanut butter would be a 1/2 times a 1/2, which is a 4th. And then down here in jar B, you have either you are going to get a chocolate chip or you're not. I guess I'll do peanut butter, right? And the chance that you get chocolate chip is 100%, and the chance you get peanut butter is 0. So again, multiplying those together, you get a 1/2 chance that you pull chocolate chip on that side, and you get a 0% chance that you pull peanut butter because there's none in there. And so there's a tree diagram that tells me, like, I can answer questions now. If we pick a cookie at random, what's the probability it's chocolate chip? Well, the probability that it's chocolate chip is this guy is chocolate chip and this guy. So to me, the probability of you pulling a chocolate chip cookie is 75%. I should say 3/4 or 75% or 0.75. So you have a 75% chance of pulling a chocolate chip cookie. Nice, right? That is just by going down the probabilities, multiplying them together, and see what you get. Now, there is a conditional probability. And how about this? Conditional probability is a little funkier. There's a given condition that you have to satisfy. So look at my next example. It says if we go up there and we do the jar cookie again, what's the chance that you draw a chocolate chip cookie if you what's the chances that you got a chocolate chip cookie that it came from jar A? So I know you got chocolate chip. What's the chance it came from jar A? You would almost think it's 50-50, but not quite, because of the fact that conditional probability says, hey, I know it's a chocolate chip. So here's how I write this conditional probability. So you write your condition as, what's the probability that you get a jar A cookie given that it's chocolate chip? You told me it's chocolate chip, right? So you can see how I write that. I'm saying, what's the probability it comes from jar A given that it's chocolate chip? Well, that is the probability of jar A and chocolate chip all over the probability of how you could pick chocolate chip cookies. So if I come up here and I look, what's the probability of a jar A, let's use a green highlighter, a jar A chocolate chip we know is a 25% chance of happening. So we're like, all right, that's a 25% chance happening. So I'm going to count that 0.25. And what's the probability of chocolate chip? Well, we already did it, but that's the yellow highlighted stuff. But the probability of chocolate chip, just in general, because you're getting a chocolate chip cookie, was 75%. So I have, if I go in fractions, 1/4 over 3/4, those fours cancel, and you get a third, or a 33% chance that the chocolate chip cookie came from jar A. And there you have it, right? That is your conditional probability. And then we'll come back and we'll do binomial. All right, and last up on this beautiful day, let's talk about binomial distributions, and I love binomial distributions. They can only be used really when you have a probability that doesn't change for each trial, and that you have two outcomes, a success and a failure outcome. So you got to be a little careful with these, but they're usually pretty fun. We'll call the probability of success P, and we'll call the probability of failure Q. And the formula for it is this. Now, the way this works is you're trying to calculate how many ways something can happen, right? A certain given number of trials and exactly how many times that trial is successful. And then you would just do the probability of the success to the how many times it had to be successful times the probability of failure times how many times it had to fail in the total number of outcomes. And you have this little combination out front of how many ways that can happen. So let's talk about a baseball problem, and hope maybe the Batter Up Sports Report can use this in their next one. Find the probability that a 340 hitter goes 3 for 5 in today's game. So what that means is if you're a 340 hitter, that means your probability of success, your p-value, is 0.34 because you're 34% of the time you're successful. Your Q value then is 0.66 because that's how often you're not successful. If you're successful 34% of the time, then you're not successful 66% of the time. And now I want to know what's the chance that a hitter goes 3 for 5 in today's game. So he's going to get 5 attempts, and what's the chances he gets 3 hits at being successful? So how do I set this up? I just go, 5 attempts with 3 being successful. The chance that he is successful is 34%, and that has to happen 3 times, times the chance that he's not successful, 66%, and that has to happen 2 times. And now I just grab a calculator and type it in, and it throws out the probability for me, and it is gorgeous. I already did it. So you can see I typed it in to my calculator, and I got 171, or a 17% chance, 17.12. 0.1712 or 17.12% chance that a 340 hitter will go 3 for 5, right? So that's how nice this is. You take whatever you're looking for, right? However many trials, however many you want to be successful, the probability that it's successful that many times, and then the probability that it's not successful that many times, and that will give you the probability of a binomial distribution. Again, binomial meaning that there's only 2 outcomes, so you got to be a little careful. Kind of like the next one. Let's keep it sports and let's keep it fun. Mr. Hahn makes 80% of his free throws. If he shoots 20 free throws in a game, so there's your 20 trials, what's the probability that he makes exactly 16? So if I'm going to set up A, I'm going to say he has 20 trials and he's going to make exactly 16. The probability that Mr. Hahn is successful, because that's what we're going for, is 80%, and he needs to do that 16 times. And the chance that he's not successful is 20%, and he's going to have to do that the other 4 times. So he's going to have to miss 4, but he's going to have to make 16. What's the probability of that? Bam. Grab your calculator and type it in. So you can do 20 math NCR 16 times 0.8 to the 16 times 0.2 to the 4. And I hit enter, and the chance that happens is a 21.82% chance. 0.2182 or 21.82% chance that he makes exactly 16 of 23 free throws. Now it gets a little more fun because what if the game's on the line and we need some points, or we need to pull away just enough so that the other team can't catch us or whatever. So we want to know what's the probability he makes at least 16, so we're guaranteed a victory. We've decided that 16 points will be our victory. Well, you just have to do this a little more than once. So the chance that you have 20 16s, he makes exactly 16. We already did it, so I'm not going to do it again. So he makes 16, but at least means he could also make 17. So then I have to calculate 17. There's also the chance that he makes 18. And so I would have to calculate 18. And so, by the way, notice the numbers changing. If he makes 18, he's missing 2. What's the probability that he makes 19 out of 20? And so I could figure out that probability. And last but not least, what's the chances he sinks all 20? And so I can go ahead and calculate his probability. And so notice the first one is 16 shots, and then 17, then 18, then 19, then 20. And since those are all good for us, we will add them all together. And so I'm going to type it in real quick, and I'll come back after this. All right, now I've gone ahead and I've calculated them all out using my calculator, and you can see that we had the 21.82% chance that he made 16. There's a 20% chance that he makes 17. There's about a 13% chance that he makes 18. There's a there's about a 5 or 6% chance that he's going to make 19. And there's only about a 1% chance that he will make all 20 shots. But since we're just curious that if he makes 16 or more, that we're going to win, look at that. We have a really good chance that we're going to win. Han is money. I mean, we got a 62%, almost 63% chance that we are going to win this game as he goes up and shoots his 20 free throws because we just needed him to make 16 or more. And that's it. That's kind of fun. Now, I will show you one thing on the calculator that I think is kind of neat. Typing in all of these would be really annoying, and so the calculator people know that. And you can see this weird binomial PDF thing on there. Binomial PDF is just really the binomial distribution, and the way you get there is you hit second distribution right up here above vars. So second distribution. If you look there, I don't want to use normal. I want to use binomial. And so there's two. There's a binomial PDF, which means tell me exactly what 16 out of 20 would be or something like that. And there's binomial CDF, which is when it adds up the first 16 or whatever free throws. So let me show you what I mean. If I want to do, let's do 18 free throws. If I want to do 18 free throws, then I would hit binomial PDF. I'd say we have 20 trials. The chance that he makes it is 80%, and I want to know that he made exactly 18 of those. And if I hit enter, you see all it really does is call up the function and put in the parameters. For those of you who don't have the new operating system, this is helpful because you can see the first number is how many trials. The second number is, after a comma, is the percent he makes it, and then the third number is how many of those shots of those trials did he actually get successful with. And if you hit enter, it spits out the 13.6 percentage. So that's calculated for you. Super neat, right? So that's what I ended up doing. In fact, I just then hit second enter and it just recopied, and I was like, okay, let me see what 19 trials. Oh, there's his percentage. And I was like, second enter and tell me what 20 is. And this got really quick and easy. So that was nice. The other way I guess I could have done this is if I go to distribution and I hit binomial CDF, that will add up from 0. It always starts from the low end. So it will go from 0 makes, so Han makes 0, all the way up to whatever I tell it the X value is. So I could say again, he's got 20 trials and his probability of making is at 80%. And then I wanted 16 to 20. So this is kind of weird. You have to be careful. It'll go 0 to whatever. So I want it to figure out from 0 to 15. And it'll put that in. It'll calculate. It's a 37% chance that he makes 0 to 15. But remember, we want 16 others, so they got to add up to 1. So I could just subtract that answer from 1. And you see, we get a 62.96% chance that Han's going to make 16, 17, 18, 19, or 20 free throws. So you can play with it. You can ask me in class, and we can talk about it more. But have a great weekend. Stay happy, and I'll see you soon.